Hello everyone. Welcome to another video in this series where we are going to be building a modern lake house which can scale to petabytes of data. In the previous video, we talked about why traditional data lakes started breaking and why Apache Iceberg became necessary. In this video, let's talk about something equally important: how to choose the right technologies to build a modern lake house. Before we start building anything, I think it's really important to understand how to pick the right technologies. Because honestly, modern data platforms are no longer about storing your files in S3. Every decision you make here, be it your compute engine, table format, catalog, query engine, eventually is gonna impact your scalability, operational complexity, concurrency, governance, cost, and long-term flexibility. A quick introduction about myself. I am a senior data engineer currently building a petabyte scale data platform at NinjaOne from scratch. Over the last several years, I have worked on distributed systems, cloud native architectures, large scale backend platforms, anomaly detection systems, and enterprise data pipelines across cybersecurity and logistic domains. So, throughout this series, I'll try to focus on how these architectural decisions actually play out in a production environment. Now, let's discuss what modern lakehouses actually need. When teams start building data platforms, they often choose technologies independently. They may choose Spark for processing, some storage layer, maybe a query engine. But the real challenge isn't individual technologies at all. The real challenge is how these systems behave together under scale. Modern lakehouses need multiple engines accessing the same data. Different systems like Spark, Trino, Flink, they should be able to safely work on the same tables without creating inconsistencies. The system should have reliable concurrent reads and writes. Readers should never see partially written or corrupted data while multiple jobs are updating tables simultaneously. System should have scalable metadata handling. Table metadata should remain efficient and manageable even with petabytes of data and millions of files. Schema evolution. Tables should support safe schema change like adding, renaming, or reordering columns without breaking pipelines. Streaming support, governance, and ideally minimal vendor lock-in. That's the lens through which we will evaluate this architecture. Now, coming to, let's choose the right processing engine. Once we decide on building on object storage, the next question becomes what's actually gonna be producing data into the lake. And honestly, this decision depends heavily on the workload characteristics. If your entire platform is streaming first, especially event driven systems with low latency requirements, then Flink becomes extremely attractive. Flink's streaming model is genuinely impressive. You get event time processing, stateful computation, checkpointing, low latency continuous pipelines, and a very sophisticated stream processing semantics. And this is exactly what you will be looking at for a streaming architecture. But the trade off is that operational complexity. Running Flink reliably at scale is not trivial at all, especially for teams which have already invested heavily in Spark infrastructure. Now, Spark, on the other hand, isn't necessarily the lowest latency engine, but it's incredibly mature. Most enterprises already have Spark clusters, Spark orchestration, observability, engineers, and existing ETL pipelines. And honestly, ecosystem maturity matters a lot at scale, especially when debugging production failures at 2 a.m. Now, Sparks give us flexibility. We can use batch ETL, micro batch streaming, ad hoc transformations, and Iceberg integrations all inside the same ecosystem. So, for this series, Spark makes the most sense, not because Spark is universally better, but because it aligns well with the architectural goals we have here: scalable distributed processing, mature Iceberg support, operational familiarity, and flexibility across both batch and streaming workloads. Now, we need to understand that even after choosing our compute, we still have a major architectural problem because we are just generating Parquet files. And as we discussed in the last video, Parquet alone doesn't solve transactions, snapshots, schema evolution, table versioning, or concurrent writes. So we need some kind of a table abstraction layer. At this point, most teams usually evaluate Delta Lake, Hudi, and Iceberg. Each one optimizes for slightly different workloads. Now, Delta Lake is extremely mature inside the Databricks ecosystem. Honestly, if your entire platform already lives inside Databricks, Delta is a very reasonable choice. The developer experience is polished, the integrations are excellent. Operationally, it's very smooth. You have to do little to no configuration at all. But the tighter you couple yourself to a specific ecosystem, the harder multi-engine interoperability sometimes becomes later, especially if your architecture evolves over time. Hudi takes a slightly different direction. Hudi is heavily optimized around incremental ingestion and record level updates. So, if your workloads involve CDC pipelines, near real-time ingestion, heavy upserts, or continuously changing records, Hudi can actually be extremely compelling. But operationally, Hudi tends to introduce more moving parts compared to Iceberg, especially once your architecture becomes large. Now, Iceberg became interesting because it focused heavily on your scalable metadata, snapshot isolation, multi-engine interoperability, partial partition evolution, and long-term table management. And personally, one of the things that I like most about Iceberg is that architecture feels very future-proof. So now we have Spark, which can write, Trino, which can query, Flink, which can stream, and everybody interacts with the same table abstraction safely. That flexibility becomes incredibly valuable once platform starts evolving over the years. Now, once we introduce Iceberg, we still need a catalog layer. And honestly, catalog choice is becoming one of the most important architectural decisions in modern lakehouses. Even we have been discussing the same for the last 2 weeks about which catalog to choose exactly. I think the industry is slowly realizing that the catalog layer is becoming far more strategic than people initially expected. Historically, catalogs were treated almost like your supporting infrastructure, but modern lakehouses are becoming increasingly multi-engine. Spark writes data, Trino queries it, Flink is streaming continuously, governance system apply policies, AI systems consume features, and now all of these systems need consistent metadata, governance, lineage, access control, and interoperability. That's why catalogs are slowly evolving into the control plane of your modern data platforms. Today, we have much newer options. We have AWS Glue, Unity Catalog, Apache Polaris, and this is not the exhaustive list. This space is evolving very rapidly. Now, let's take a look at what each of these catalogs give us. Okay, let's first look at AWS Glue. Now, Glue works extremely well inside your AWS native environments. It's managed, integrates naturally with S3, works very nicely with Spark, Trino, Athena, and it reduces a lot of operational overhead. So, if you're already inside the AWS, think you can think about choosing Glue. Now, Unity Catalog is honestly very compelling if your organization is already standardized inside Databricks. It has governance, lineage, access control, centralized management, and the experience is extremely polished. But again, there's always a trade-off between convenience and ecosystem coupling. If your architecture is intentionally multi-engine and open, that's something you need to think about carefully. There is an open source Unity catalog as well, but it lacks a lot of features like your row level security, data lineage. So if these features are required, you should look into some other catalog. Now, Apache Polaris is also becoming very interesting, especially because it pushes you toward open catalog interoperability, multi-engine interoperability, and decoupled governance, which aligns very well with where modern lakehouse architectures seem to be heading, especially for organizations trying to avoid becoming tightly coupled to a single ecosystem. For this series, AWS Glue makes the most sense, mainly because it's fully managed, integrates naturally with AWS, and it works very well with the stack that we are building. We'll do a separate deep dive video on catalogs later because honestly, this topic alone deserves its own discussion. Now, once the data lands into your Iceberg tables, we still need a query layer. And again, there are multiple regional choices here. Spark SQL works very well, especially when you are querying and transforming your data together. But Spark was fundamentally designed as a processing engine first, not necessarily an interactive analytical engine. Then you have Athena. Athena is extremely convenient, especially for serverless exploration. You don't manage infrastructure, you simply query the data. And honestly, for many organizations, Athena alone may already be enough. But once workloads become larger and interactive, or it started involving multiple systems, Trino becomes extremely compelling. Trino is very fast for distributed analytical workloads. More importantly, it's federated by design, which means that it can query Iceberg, Postgres, Kafka, Elasticsearch, MySQL, and many other systems through a single SQL layer. That flexibility becomes incredibly powerful in modern data platforms, especially when your architecture is becoming increasingly distributed over time. So for this series, Trino becomes our analytical query layer. Now, the final architecture, what we will build, as we discussed in the previous video, we will use Spark as our writer. We will use Iceberg as our table format. We will use AWS Glue as our catalog. We will be storing the data into S3, and we will be using Trino for our analytical query layer. So this is the stack that we will use throughout the series. Most importantly, the architecture stays open and multi-engine, and honestly, flexibility becomes incredibly valuable once platforms start evolving over several years. Now let's say there is a DuckDB that you want to introduce over your Iceberg tables. You can do that very easily. So it's very open for new technologies, new systems that you want to operate on. Now that we understand the architectural decisions behind the stack, in the next video, we'll finally start building. We'll configure Spark with Iceberg and AWS Glue. We will create our first Iceberg table. We will ingest the data using Spark and start exploring how Iceberg metadata actually works under the hood. Thank you very much, and let's see you guys in the next video.